Good evening. Thanks for joining me on this fine Monday night. We've got 5 people viewing, it looks like. That is honestly more than I expected. So thanks for being here to listen to me talk about some really cool math. So I just wanted to mention a little bit about the purpose of these streams that I'm doing. Obviously, I want to do some review to help you prepare for exams. And understand the significance of topics that you've covered in class. But also I want to give you a little bit of a preview of some upcoming material, things that you'll see later in Calc 2, things that you'll see in Calc 3, if you're sticking with us for another semester. And I want to talk about some of the really cool applications of calculus. Unfortunately, just the reality of our schedule is we don't always have time to do the really cool stuff in class, but I think you all deserve to see the really cool stuff. And lastly, as I mentioned in the announcement on Canvas, I think in Calc 2 especially it can be easy to lose the forest for the trees, and it can be challenging to understand what the big picture is. So I want to help try to contextualize the things that you're learning in Calc 2, help you see the big picture of calculus. As always, ask me questions. You can send me a message in chat. If you don't want to send a message in chat here, you can send me an email directly. I will put my email address in the chat in case you want to copy that. I will keep an eye on my email during the stream. And then the last thing I want to mention is that there are some ads on Twitch. It seems that I'm not able to disable them completely, but I do have a large degree of control over when they run, so I'm going to do my best to make sure that you never miss anything. I think maybe during the review session last time, some people had the experience of asking a question and then an ad cut them off, so they couldn't hear the answer. But I think I can make sure that that doesn't happen. So I guess let's get started. The first thing that I want to talk about today, and let me show you my iPad. I want to show you how to evaluate this integral, the integral from negative infinity to infinity of e to the minus x squared. This is called the Gaussian integral. And this e to the minus x squared, this function is called the Gaussian distribution, or the normal distribution. If you've ever heard of a bell curve, this is the function for that curve. This is probably, if I had to pick the single most important definite integral in all of existence, it might be this one. I'm curious. Let me know in the chat. Has anyone seen this integral before? It's not something I cover in Calc 1 or in Calc 2 when I've taught it, but I'm curious if anyone here has seen it before. If you have, let me know. So first of all, why is this important? And let me actually sketch a graph of this function, so we have a picture to look at. The function e to the minus x squared looks something like this. Again, that's that normal distribution, the bell curve. And we're trying to compute the integral of this from negative infinity to infinity, so the area underneath this entire curve. And the reason it's so important is that this normal distribution pops up all over the place in math, science. It's super important in statistics. Ben, do I mind going through center of mass problems at some point? Yeah, I'd be happy to talk through that. I want to go through this first, but if you stick around later in the stream, I'd be more than happy to talk about center of mass. So this normal distribution pops up all over the place. Yeah, I mean, statistics, right? Just the study of how do we draw conclusions from data. This is sort of the most important distribution. And I actually want to show you a cool little demonstration of why this distribution is so ubiquitous. Here we go. So this is from the statistics course I'm teaching. What this is showing right now is if you had let's say you flipped a coin. Well, if you flip a coin, it's usually a 50% chance of coming up heads and a 50% chance of coming up tails. So this graph here is showing you the probability, if you flip the coin 3 times, the probability of getting 0 heads, 1 heads, 2 heads, or 3 heads. And if I increase the number of coin flips, like let's say we flip it 10 times, you can see it's most likely to come up heads 5 times, of course. But there's a significant chance that you get 4 heads or 6 heads out of the 10. But if I increase this number to 50, that function looks quite a lot like this e to the minus x squared. And actually, yeah, and then the more I increase this, the more and more it looks like that Gaussian function. And there's a very good reason for this. It's called the central limit theorem. It says that sort of even if you start with something like flipping a coin, which is not inherently governed by normal distribution, if you do it a bunch of times and add up the results, you always end up with something that's approximately normal. So that's a little bit of why this function is so important. But integrating this function is very hard. And you might think, what's the big deal? I've taken Calc 1. I remember the fundamental theorem of calculus. I just need to find an antiderivative. And then I plug in infinity, plug in negative infinity, and subtract. F of b minus f of a. Okay, you can't literally plug in infinity or negative infinity, so we need to rewrite this as this is an improper integral, so we need to rewrite it with some limits if we want to be technically correct. But that's the idea. Just find an antiderivative, and compute f of b minus f of a. The problem is, and your instructor in Calc 1 might have mentioned that if they ever talked about this function, there's no antiderivative for e to the minus x squared. At least there's not one that you can write down in terms of any of the functions you know about, like trig functions, exponentials, logs, polynomials, rational functions, roots. Basically, you can't write down an antiderivative without using an integral inside of the antiderivative. So it doesn't help us. So it's a very strange fact that even though we cannot possibly write down an antiderivative, and this is just it's not that no one has found an antiderivative. We actually have proven that there is not an antiderivative. So even though we can't do that, somehow, magically, we're able to integrate this thing from negative infinity to infinity. But like if you wanted to integrate it from 0 to 1, nope, you cannot do that. Now later in the semester you'll learn how to do that, but you won't be able to write down the exact value. You'll only be able to write down an approximation, and later in the semester you'll learn some techniques to approximate this very efficiently. That's one of my favorite things that you learn about in Calc 2. But for now, we can actually give the exact value using some cool ideas. And if you haven't seen this answer before, get ready to be blown away. It's surprising. Okay. So the main idea of how we're going to go about this, and the reason that I'm doing this now, and that it's gonna help. It's gonna also serve the purpose of doing some review of recent topics, which is that we're gonna approach this by finding the volume of a solid revolution. Okay, so. we're going to find the volume of the solid of revolution. So I want to rotate this curve. Let me start sketching the picture. Basically what I'm going to do is I'm going to take my normal distribution, my function, which looks something like this, and we're going to rotate this around the z-axis. I've got this rendered in GeoGebra. Maybe let me show you that. Oops. I thought I had it. Hang on. Let me try to find this. Okay, sorry. It disappeared, so... Oh, wait, recover. Well, bring it back. There we go. Okay. So it looks something like this. It's kind of like a three-dimensional Gaussian function. So we're going to find the volume of this shape. We're going to do it two different ways. And setting them equal to each other is what's going to evaluate this integral for us. Because at this point it should not be obvious to you why the volume is going to tell us about this area. So this curve, I guess, if I just want to describe this curve, I could describe it as z equals e to the minus x squared, and x equal, oh, no, that's y. That's y. And x is equal to 0. So that's describing this curve right here. The z value is equal to e to the minus y squared. So the y value is determining the height here, and the x value is 0. So we're in this plane, x equals 0. Describing it in equations is a little weird, but I hope you are understanding this idea that I'm taking this Gaussian curve and rotating it to make this solid of revolution. Okay. And we're rotating this around the z-axis. Alright, so method 1. We could use slices perpendicular to the, let's say, to the y-axis. Let me go with x-axis. And again, I'll show you in GeoGebra what this looks like. We have our curve here. And I'm going to slice it perpendicular to the y-axis. And I've also included the intersection of this plane and the function, so you can see right, that black curve is a normal distribution. It's the function e to the minus x squared. But now if I slide the plane, so we look at a different slice, that slice there is still, it turns out, it's still the Gaussian function. And I'll show you the algebra there, but the point is I'm going to make this volume by adding up the volumes of a bunch of these tiny little slices. Okay, so we're going to slice it, let's say, at some x value. No, I want to slice it at some y value. Okay. I'm going to slice it at some y value, so we're going to intersect this curve, or this plane, with the shape. And as I hope I convinced you in GeoGebra, the resulting shape is going to look like a little Gaussian function. Okay, so I'm picking a particular y value, in order to be able to understand this, I should write down what the function is, what the z value is at any given x and y. Now, the point of rotating this around the z-axis is that the height only depends on how far away we are from the origin. It's circularly symmetric. Right, you can see that symmetry here. The height of this bump only depends on how far away you are from the origin. And how far you are away from the origin, you will talk a lot about this coming up later this week, I think, in Calc 2, when you talk about polar coordinates. And the distance from the origin is the square root of x squared plus y squared. That's because if we look down from above, if we look at some point, at an x value of x and a y value of y, the Pythagorean theorem tells us that the distance from the origin is the square root of x squared plus y squared. Now, when you're on this portion here, the part that's going to get rotated, the height, the z value, is e to the minus y squared. And here, that y value is the distance from the origin. So we're supposed to do e to the minus the square of the distance from the origin. That means that the equation of the surface is z equals e to the minus x squared plus y squared. If my explanation of why this is the equation isn't totally making sense, that's all right. We can still figure out how to integrate the function if you'll just trust me that this is the equation. I guess you can see that it makes sense, at least, since when we're on this slice, because x is 0, if x is 0, this just reduces to e to the minus x squared. Sorry, e to the minus y squared, which is how I defined the curve originally. And if we're on this portion of the surface, meaning that y is 0, then this just reduces to e to the minus x squared. So in either of these directions, we just get this Gaussian function. And it's going to be true in any direction you look at. Okay, so this is the function. Now let's find the volume by slicing it up. So what I'm going to do is I'm going to integrate over all the possible y values, and so that makes an integral with respect to y, and y is going to go from negative infinity to infinity. And then at each y value, I'm going to get this slice, and I need to find the area of that slice. Well, I guess if I'm thinking about breaking up this volume, it's going to be a bunch of really thin sort of cross-sectional volumes. The volume is the area times the thickness of that cross-section. The thickness of the cross-section is the dy. And what we need to integrate here, or what we need to put inside the integral, is the area of the cross section. Okay, so again, if I've lost you a little bit with working out the equation of the surface, I hope this at least is familiar. This is how you found volumes by cross sections a week or two ago. You integrate in one direction, and then the thing that you integrate is the area of the cross-section. Okay, so how do we find that area of the cross-section? That area I'm talking about looks kind of like that. My picture's not the best, but maybe if I go back to GeoGebra, I'm looking for the area underneath this curve. Well, how do I find the area underneath a curve? I'm going to use an integral. Most of the problems that you saw in class with cross-sections had very simple areas for the cross-sections. You might have been told that all the cross-sections were squares or triangles or semicircles. Here, yeah, that's like, it's another Gaussian function. So this area, the area is going to be the integral as x runs from negative infinity to infinity, right? I've picked a particular y value, and now this area is I'm looking at what happens as x runs from negative infinity to infinity, and it's the area underneath the curve is just the integral of the function. The integral of the function, well, we've said the function is e to the minus x squared plus y squared. Now, I can simplify this a little bit. One thing I can do We're doing Calc 3 already? Kind of. Yeah, I'm sort of giving you a preview of Calc 3 ideas, but expressed in the language of Calc 2. Right, this is a Calc 2 idea, that we can find a volume using cross-sections. It's just that to find the area of that cross-section, we're going to need to do an integral. But I hope that I'm convincing you that maybe Calc 3 isn't so scary. So this is just a property of exponents. I guess I distributed the minus sign, and then an exponential of a sum is the product of the exponentials. But then I'm integrating with respect to x, and I have this e to the minus y squared term. But since this doesn't contain any x's, this is a constant. I mean, it depends on y, but as far as this integral with respect to x is concerned, it's a constant. It can come outside of the integral. That e to the minus x squared comes outside of the integral, and we're just left with this integral of e to the minus x squared. Now, of course, that's the thing we're trying to find. We don't we don't know what this is, but you'll see how it all fits together. Okay, so the volume we said was the integral from negative infinity to infinity with respect to y of the area of the cross-section. And the area of the cross-section is this. So I'm just going to copy this here. Okay, so we've got an integral inside of an integral. But remember how I just pulled this e to the minus y squared out of the integral because this is an integral with respect to x and this doesn't have any x's in it? I'm going to do the same thing. Again, this is an integral with respect to y, but this piece doesn't have any y's in it. So this piece can come outside of the integral. And what's left inside of this integral with respect to y? Just the e to the minus y squared. Alright, this is better, Before we had an integral inside of an integral, which is confusing. Now I just have two integrals getting multiplied together. That's fine. I mean, it's still hard, but at least at least I don't have, well, this would be called a double integral. The next change I'm going to make is I'm using the variable y here, but that variable, this variable y is called a dummy variable. It doesn't matter what letter you use. I could write e to the minus u squared du. I could write e to the minus a squared dA. I could even write e to the minus x squared dx. I just have the same thing here twice. It's being multiplied with itself. So in other words, the volume is the square of this integral that I am trying to evaluate. So that's the reason that I'm considering this volume, is because if I knew the volume underneath this surface of revolution, I could take the square root and then I would know the integral that I'm trying to find. BP, when you get to the review session, would you mind going over a cylindrical work problem? Oh yeah, I'd be happy to do that. Yeah, forming the cross-sectional area in the work integral. Yeah, absolutely. And plotting parametric equations and calculating arc length, if there's time. Yeah, if there's time. Parametric equations, you did that today, I believe. Arc length is tomorrow on the calendar, right? Okay, so if I knew the volume, I would take the square root and I would get this area of the Gaussian integral. But I don't know the volume. So how do I find the volume? Fortunately, I have another method of finding volumes. I went about it here using cross-sections. But what's another method of finding volumes that you've learned about recently? Well, you probably learned about a couple methods. Disks, washers, shells. All of these methods that are designed to take advantage of this rotational symmetry. The fact that this isn't just a random three-dimensional shape. We made it by rotating this curve around the z-axis. So we're going to use this other method in order to actually numerically find this volume, and then we'll take the square root and we will know what the integral is. How do you know when to use shells or washers? Like, how do you know which one to pick? That's a really good question. So let's talk about that briefly. I think I want to say shells versus disks and washers. Disks and washers kind of go together, but shells are a very different thing. And there's a really nice way to think about this, to think about the difference. And honestly, I didn't really even realize this until a couple of years ago, which is strange because I took calculus like 15 years ago. I should have realized this a long time ago. All right, so let's say I have this curve, and I want to take this area and rotate it around the y-axis. All right? I'm going to rotate this shape around the y-axis, and I'll make some volume, and we'll try to find the volume. Or we'll think about how we would. We're not actually going to do this. I'm going to draw the same shape, rotate it to make the same volume. But if you were just finding this area of the shape, not even thinking about volumes, just finding the area, you've kind of got two different ways to do this. One method would be to look at any individual x value and then make that little rectangle. And I guess really what I mean is break the whole shape up into, you know, a bunch of thin vertical rectangles. This is classic Calc 1 stuff. This is how you were introduced to the idea of an integral. You find the area by breaking the volume, or breaking the area up into a bunch of small vertical strips, and then it's easy to find the area of each because it's a rectangle, so you do width times height. The width is going to be the dx, the height is given by the function, so you multiply the height of the function, or the height, which is the function, by the width, which is dx, and then you add them up, and we use a fancy s as in sum for adding them up, and there you go, there's the integral. But there's a second way that you could do this. You might or might not have seen this in Calc 1. We only had a day for areas underneath curves in Calc 1 last semester, so probably you didn't see it there. But I would guess you saw this in Calc 2, maybe. Someone in chat, you can tell me if you saw this other approach. But the other way to go about this is, you know, why were the rectangles vertical? There's no reason they have to be. I could just as well split this up into a bunch of short horizontal rectangles. There's absolutely no reason that they have to be vertical. They could just as well be horizontal. In this case, you integrate with respect to y, and again, you do the width of the rectangle times its height. In this case, the width is going to be some function of y, like you say what the y value is, and then you can find the width by looking at whatever the x value is on the curve. So I guess here you would describe the curve as y is a function of x, and then here, maybe let me call it x is a function of y, but I'll call it g. So you would integrate, well, you would take the width, which is g of y, here, let me write this out. Before we said the area was the integral of f of x dx, and here we're doing the width of the rectangle, which is g of y, times the height, which is dy. Multiply those together to get the area of the rectangle, add them up across all the rectangles, and there you go. So yeah, could you all let me know, did you see integration with respect to y when you talked about areas of curves in Calc 2? You did both methods. Awesome. Okay. So you might be thinking, what the heck does this have to do with the question about shells versus discs or washers? Well, I want you to think now about what happens, not to the whole area, but just to that one little red rectangle when you revolve this surface, revolve this area around the y-axis. Just, yeah, imagine spinning this whole thing around this axis and think about what's going to happen with this red rectangle. Well, as you spin the whole thing around, that red rectangle is going to make a disk. But now look at this green rectangle over here. When you spin this purple area around the y-axis, what's going to happen to that purple area? Sorry, what's going to happen to the green rectangle? I'm doing my best to draw these 3D pictures here, but it's not perfect. When you spin that vertical strip around, it's going to make a cylindrical shell. So really, the difference between shells and discs or washers, the difference is just, are you splitting up the original region that's getting rotated? Are you splitting it up into a bunch of vertical pieces or a bunch of horizontal pieces? That's the only difference. So the way that I go about actually deciding which method to use is, instead of thinking immediately about the surface of or the volume of a revolution, I just think about the shape, the two-dimensional shape that's going to get revolved. And then I think about, is it going to be easier to break this up into horizontal or vertical pieces? And which one is easier depends on it depends on what this curve here is. Like, if I have a region formed by a line and a parabola, if this is my region, I definitely want to go this way. Because then, well, the height of this rectangle is the y value from this line minus the y value from that parabola. If I try to go the other way, I run into a problem. You know, you can still do this, it's just going to be harder. The problem is that some of the rectangles, the width is going to come from the x value on this line minus, an x value of 0. But for other rectangles, like the bottom one here, the length is going to use an x value from the parabola, and that x value of 0. So you're going to have to split this integral up into two pieces if you want to do horizontal strips instead of vertical strips. So that's how I decide what method to use, is I look at just that two-dimensional shape and I think, is it easier to split it up into horizontal strips, or is it easier to split it up into vertical strips? And then once I've decided that, then I'll start thinking in 3 dimensions. I'll picture those strips, horizontal or vertical, whichever one I decided to go with, and then think about what happens when I rotate those strips around the whatever axis I'm rotating around. And I think it's important to actually think through this every time, instead of just trying to memorize, like, vertical strips gives you shells and horizontal strips gives you discs. Because if I were to rotate around the x-axis, it would be flipped. If you were to rotate around the x-axis, a horizontal strip is going to become a shell, and a vertical strip rotated around the x-axis would become a disc. So, does that help? Does that answer your question? Is there more I could say to help clear this up? Okay, so we're going to try to find this volume the volume underneath this rotated Gaussian function, because if we can find that volume, the work we've done so far tells us that if we take that and take the square root of it, we'll learn the value of this Gaussian integral. So we're going to, I suppose we should apply this logic that I've just told you about and decide what method to integrate this with, shells or disks or washers. So looking at the picture here, I think I definitely want to I want to split the area up into vertical strips like this. And when I split them up into vertical strips and rotate them around, those vertical strips, sorry, that picture is terrible, but the vertical strips rotated around will make cylinders. The reason is just that, well, the height of that vertical strip is e to the minus, let's see, I'm on the y-axis here, so it's just e to the minus y squared. Shells, yeah. Turn one nut peggle. I agree 100%. We're going to use shells here. The other way, the problem is just what what is the width of this rectangle? Given this z value, I would need to find the corresponding y value. I mean, we could solve, right? I guess log z is minus y squared, so y is the square root of minus log z. I just don't want to deal with a square root and a log. I'd much rather deal with this function here, e to the minus y squared. Okay, so I'm going to integrate I'm going to find the volume under the Gaussian surface, which once again is e to the minus x squared plus y squared, is the integral. It's going to be an integral with respect to y. It could be with respect to x. It doesn't really matter, but I'm going to look at all of these y values here and think about the corresponding little vertical strips and the volume that they contribute when they get rotated around. So now what are my bounds? I'm only integrating from from 0 to infinity. I don't need to integrate from negative infinity to infinity because like this strip over here, that's already accounted for by this strip, because this is going to get rotated around. So I would be double counting the volume if I looked at all of these y values. So we'll integrate from 0 to infinity. And what's the volume of that circular, or of that cylindrical shell going to be? Let me sketch a cylindrical shell. And again, I don't memorize formulas. I just sort of think through the geometry, because I find it easier than trying to memorize all the different formulas and figure out which ones to use when. So the volume of this cylindrical shell, let's say that it has height h and radius r. Well, the volume, the idea here is to imagine cutting through the cylinder on one side and then unwrapping it to get a rectangular prism. It's not exact, but if it's a very thin a very thin shell, this is a good enough approximation. So I'd get a rectangular prism. The height, I guess I should say what the thickness is. The thickness here is the dy. So I'm just multiplying together the 3 dimensions for the shell. The height is h, the thickness is dy. The hardest one is, well, when you unwrap it, how far around does that go? Well, that's 2 pi r. Green onions. Yep. Yeah, if you slice through just one side of a green onion and roll it flat, it's basically a rectangle, and the width of that rectangle, yeah, this is a great vegetable to picture. The width of that rectangle is the circumference of the onion before you cut it open. Okay, so in our case, the cylindrical, the radius here, well, that's what we're calling y, right? That y value is that's the radius of our cylindrical shell. So I'm going to have 2 pi y. And then what is the height? It's just e to the minus y squared. Remember, the height of the surface is e to the minus x squared plus y squared. But I'm just looking at all these little vertical strips here. The height, to find the height here, I'm on the y-axis. So I can say my x value is 0, and then the y value is whatever the y value is. But yeah, the point is, for that little strip, the x value is 0. So the height is just e to the minus y squared. And just a little bit of a preview of where you're going to go later this week with cylindrical coordinates. Instead of y, I could just use r. The point is just that, right, this is the distance away from the origin. And you know, even without thinking about the geometry of this, it's totally fine for me to rewrite this as this, because as we said before, the variable of integration is a dummy variable. It doesn't matter if I call these things y or r, x, u, whatever I want to. But I like r because it signifies the distance from the origin. Okay. So we need to integrate this function, but this is actually pretty easy. It looks kind of like the Gaussian integral that we're going to such lengths to integrate, but there's a crucial difference, which is that it has this extra factor of r, and that makes it very easy to integrate. Whereas without the r, it is, well, extremely hard. We've already been talking for almost an hour about how to do this. We are almost done. We were so close, like 5 more minutes. Okay. So how do we do this? U substitution. I'm going to set u equal to r squared. You know what? Let's make this even a little bit easier. I'm going to make u minus r squared. So du is minus 2r dr. So the volume is going to be, well, we said it was the integral from 0 to infinity of 2 pi r e to the minus r squared. I'm trying to get a 2r dr, a minus 2r dr. So let me pull the pi outside. So I just pulled this pi outside. That leaves me with a 2r, but I want a minus 2r, so I also need to throw in another minus sign, which I'll put outside. And then I have e to the minus r squared dr. This is looking great. I have minus pi. And then, yeah, e to the minus r squared is e to the u. Minus 2r dr is du. I made a mistake here. It's a very common mistake, which is I did not convert the bounds. Well, let's do that. So when r is 0, that's the original lower bound, u is minus 0 squared, which is still 0. But when r is infinity, which is the upper bound, and okay, this is maybe not technically correct, right? R equals infinity. I should talk about limits if I want to be careful. But minus infinity squared, u is going to negative infinity. So actually, when I convert from r to u, I need to re-express the bounds in terms of u, and those bounds are going to be 0 to minus infinity, which feels a little bit weird to integrate from 0 to negative infinity. We're going backwards. So I'm going to switch that to negative infinity to 0. I can switch the bounds as long as I also throw in a minus sign, or get rid of a minus sign. Okay, and let's be really careful here. Do this improper integral properly by rewriting it as the limit as a goes to negative infinity of the integral from a to 0. See, this is a great problem because we're reviewing lots of great things. We're reviewing improper integrals, volumes by cross-sections, volumes by shells, u substitution, and we're getting a little bit of a preview of polar coordinates in Calc 2. This is just the absolute best calculus problem that you'll ever find. Okay, so this integral is the easiest one we've seen yet. We find an antiderivative, which is e to the u. We plug in 0 and a and subtract. E to the 0 is 1. And then as a goes to negative infinity, e to the a, that's going to go to 0. Okay. So what was the point of doing this? Well, we said that the volume that we've been computing is equal to this Gaussian integral squared. Right, so the Gaussian integral squared is equal to the volume, but we just showed that the volume is pi. And that tells us that the integral from negative infinity The integral from negative infinity to infinity of e to the minus x squared is the square root of pi. There we go. Again, let me just remind you how crazy this is. There's no antiderivative for e to the minus x squared that you could possibly write down that doesn't already have an integral sign in it. We cannot integrate this thing from 0 to 1, from 1 to 2, anything other than negative infinity to infinity. But we can do just this one definite integral, and it turns out to be the square root of pi. Why? Why is there a pi here? Look at this curve, e to the minus x squared. What does this have to do with circles? Why is there a pi showing up here? This is just crazy. Anyway, I think this is maybe the coolest math fact out there. There are a lot of cool math facts. That's a bold statement, but it's definitely in my top 10. Okay. Thanks to everyone who has stuck around and listened to me talk about this problem that I think is so cool. Now I'll return the favor for you all listening to my cool problem by answering some questions, maybe going over some topics that folks have already asked me about. People asked me about center of mass, parametric equations, cylindrical work problems. So why don't we take a break, though, because we've been talking about math for an hour. And sometimes when I get talking about math, I forget to take breaks now and then. So why don't we take a 5-minute break or so. If you asked me a question earlier, ads, great question. Turn one that peggle. Yes, I'm going to run a couple ads, and just the reason is that if I run enough ads, like 3 minutes per hour, then you all don't get the ads when you join the stream for the first time. So in case anyone's joining us right now, I'd like them not to get ads. So I'll run a few ads during our 5-minute break, but go rest your eyes, don't think about math for a few minutes, drink some water, rehydrate. If you asked me a question earlier about a topic you'd like me to cover, send me another message to let me know that you're still here, still interested in that topic. If you have any particular questions or problems you'd like me to take a look at, that could be helpful. Otherwise, I will just open this calculus textbook over here and pick out some cool problems. But yeah, let's take a break. It's about 9, it's almost 9:04, so let's come back at 9:09 to do some more calculus. See you in a few minutes. right, welcome back. So, I'm gonna answer some of the questions from the chat. So, a while back, Ben asked about center of mass problems. So, let me pick out a good center of mass problem. And as I mentioned earlier, I want to try to help you understand the big picture of calculus, Calc 2 specifically. The way I think about the point of calculus as a whole is the idea is to solve a really hard problem by instead solving an easy problem, and then basically using a limit somehow to turn the easy thing into a solution to the hard thing. Like for derivatives, the point is we wanted to find the slope of a tangent line, or the slope of a curve, that is. That's hard to do, but the slope of a line is easy. So we found slopes of secant lines and then used limits to turn that into the slope of a tangent line. For integrals, we're trying to find the area underneath a curve. That could be a hard thing to do if the shape is, if it's not a very simple shape, but areas of rectangles are easy. So we find a bunch of areas of rectangles, and then we use a limit to turn that into the area underneath the curve. So the overarching theme with pretty much all of these applications of integration that we're learning about, center of mass, moments, work, even volumes of surfaces, volumes of revolution, arc length, and all of these, we're breaking the hard problem up into a bunch of tiny pieces, where each of the tiny pieces is easy to work out the answer for, and then we're adding up all of those answers from the tiny pieces, and the way you add up a bunch of tiny things is an integral. That's the unifying theme. We think about small pieces where the answer is easier to find, and then add them up with an integral. So let's think about a center of mass using some integrals. I guess, would you all prefer that I talk about a center of mass or just a centroid? Like the center of the region? The difference is just about multiplying by a density. But other than that, it's similar to think about areas or mass. I don't know. Do you all have a preference? Ben, you were the one who asked about this originally. Do you have a preference? Are you still here? Okay. Let's do center of mass, but I'll just use a constant density. I'm just specking out a problem here. I hope it's interesting. Not too easy, not too hard. let's suppose that this shape, there's a technical word like lamina or something, but I'll just call it a shape. And let's suppose it has constant density rho. Okay, the first thing that I'm always going to do is sketch the region. Okay, so y equals x plus 3 looks something like this. Slope of 1, y-intercept of 3. And then y equals x squared is going to look like this. I might have made a mistake picking this problem. These lines, these curves don't intersect in nice places. Oh, share screen. Thank you for the reminder. Here we go. This is not nice. I'm regretting this. Trying to think if I can just shift the line a little bit to make this work out more nicely. Sorry, this is what happens when I just pick a random book, or a random problem out of the book. We should be able to handle this. All we need to do is solve a quadratic equation to find these coordinates. I don't want to. All right, I'll be brave. I'll do it. So I'm going to set x squared equal to x plus 3. Bring everything to one side of the equation, and then I'll use the quadratic formula. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a let's see. Since when do we have adds? Yeah, they're there are ads here now, but I am doing my best to make sure that they don't run while I'm actually talking about something. If anyone has gotten an ad while I was actually talking, let me know, because I'm still trying to figure out the system. But I ran a few of them during while we were taking a little bit of a break, so that they wouldn't interrupt me while I'm actually talking. Mean Machine Rex, I am a professor. Are you a student here at CU? If not, I'm curious how you came across the stream. But yes, I teach here at CU. I've taught Calc 2 at Boulder, although I'm not teaching Calc 2 here currently. I'm just doing this for fun, because I think Calc 2 is a neat class. Okay, so this comes out to, let's see, 1 plus 12. So 1 plus or minus the square root of 13 over 2. Does this make reasonable sense? I'm going to compute 1 plus the square root of 13 over 2. That's about 2.3. Oh yeah, 2.3. I believe that based on my rough sketch. Okay, so that seems reasonable. So the first thing we need to do to find the center of mass is to find the total mass. And, intuitively, why should it make sense that you need to find the total mass? Well, because finding the center of mass is finding an average, right? It's the average x position of the shape. Like, if you broke this up into a bunch of little tiny pieces, if you broke the whole shape up into a bunch of tiny pieces, and listed off all their x-coordinates and all of their y-coordinates, and if you averaged all the x-coordinates and then averaged all the y-coordinates, that would be the center of mass, approximately. It's only approximate because, I'm breaking these up into a bunch of finite pieces. It's not, it's the same sort of thing as with integrating by finding the areas of all the little rectangles. If I want to get the center of mass exactly, I'd need to use infinitely many small pieces. And, that's where the integral comes in. But that's the idea, is that we're averaging the x-coordinates of all the little pieces that make up this shape. So how do you find an average? You add up all the things and then divide by the total number of things. Right? That dividing by the total is why, in this case, we're going to need to divide by the total mass. Don't have training in math, but you're a lifelong learner. Well, I'm glad you're here. We're honored to have you here with us, talking about some cool math. So the total mass of the region. I'm going to end up dividing by this. So once again, I am going to split this up into a bunch of thin vertical strips. Each specified by an x-coordinate. And we're gonna write down the mass of the strip at x, and then doing this integral just adds up all of the strips. And like I said, the point of the integral is to break down this complicated problem into a bunch of simpler problems. Finding the mass of this little rectangular strip is much easier. And it's this region isn't quite a rectangle, but the point is if it's a really small region, I can pretend it's a rectangle, and I'm not going to be off by too much. And when I take this limit of making these strips thinner and thinner, I get better and better results. And that limit, that's the integral, using more and more thinner and thinner strips. Okay, so what is the mass of that strip? It's the area of the strip times the density. Area times density is going to give us mass. The density I've just said is a constant, which I'm calling rho. And then the area is I'm going to put the rho first because the area includes the dx. The area is the height times the width. The height is that y-coordinate minus this y-coordinate, so x plus 3 minus x squared. And I guess this isn't quite correct. It's actually the whole thing, including the dx. So that's the density, and then this is height times width, which gives us the area. Okay, so this is how we compute the total mass. Oh, and I guess we need bounds. We're going from here to here, and those bounds come from that integral, or from that equation that we solved. So it's positive 1 minus root 13 over 2 to 1 plus root 13 over 2. And we're, those bounds I guess should be on this integral also. I'm going to pull that constant rho outside. And then I have x plus 3 minus x squared. I'll find an antiderivative. Plug in the bounds, subtract. This is just, I think I made the wrong decision. Let's see. Yeah, I mean, this is going to get ugly if I try to plug this in. So maybe let me restart with a new example to actually find the center of mass. But this was still instructive, I think, finding just the total mass. And again, the idea is that you break it up into small pieces, and each piece individually should not be too hard. If you have questions about this example, let me know. And then why don't I just talk a little bit, just very briefly, about how you find the center of mass, why the formula is what it is. And maybe I won't go through a specific example there unless that's what folks want to see. Otherwise, I can address some of the other questions. Like someone asked about a cylindrical work problem. I think that would be a really good thing to do. But let's suppose we have a region maybe it's defined by two curves, f and g. And it's going to go from A to B. And let's find the center of mass. So the x-coordinate of the center of mass, well, remember, what's the philosophy? We're going to break this down into individual strips where it's easy to figure out what they contribute, and then just add up all the results. That's the big picture idea of all of these applications of Calc 2. So I'm going to look at this little strip. Remember, center of mass, I'm thinking about averaging the x-coordinates. So I add up the x-coordinates of all the pieces and then divide by the total number of pieces. Now that's not quite right. We're not doing the number of pieces here because there aren't actually like discrete little pieces. But we add up. Well, yeah, if you were to imagine breaking this into a bunch of pieces, right, the bigger the strip is, the more little pieces there would be in here. But also, if if the strip is really heavy, like the density matters too. If the strip is heavier, then it's going to affect the average more. But let's just suppose that it's a constant density. So I'm adding up the x-coordinates of all the pieces. So the x-coordinates in this rectangle are x, but if this piece is taller, again, there are more little pieces then. How many little pieces are there? It's going to be proportional to the area of this rectangle. And the area of that rectangle is f of x minus g of x times dx. And as I said, the amount that this contributes is really proportional to the mass. So let's break this down. This is the area of the little rectangular strip, and this is the mass of the strip. And the point is that for all the little pieces, we're adding up their x-coordinates. So So however many little pieces there are, which is sort of proportional to the mass, it tells you how much matter is in there. For all of those little pieces, we're adding up that same x-coordinate of x. And to add them all up, we do an integral. But when you do an average, you don't just add up all the things, you divide by the total number of things. What's the total number of things? It's how much matter is in this region. That's the total mass. Not just from this strip, but the total mass from all of the strips. And we've already discussed an example of this. Okay, so this should match up with the formula for center of mass that you were taught in class. Are there any other questions about center of mass? I'm inclined to move on and do an example of work with a cylindrical tank. But if there are any questions, I'm happy to talk about this a little bit more. Okay, let me do an example with work in a cylindrical tank. So let's pump some water out of a cylindrical tank. Let's say it's 50 feet long. Let's say the ends are semicircles with a radius 10 feet. And let's say the tank is filled to a depth of 10 feet. sorry, of 7 feet. Okay, so I'm going to sketch a picture of this as best as I can. Let me draw a big circle and then erase the top half of it. And then let me make a copy. So here's our tank. Alright. So let's suppose that it's filled up to 7 feet, which is going to look something like this. It's filled up to a depth of 7 feet, but it is 10 feet tall. Now, as I've said before, the whole idea with these applications of integrals is to break up the problem into a bunch of tiny, easier problems and add the results together. So, instead of finding and thinking about all of the water at once, I'm just going to make one little horizontal slice . And I'm just going to think about how much work it takes to lift that one little red slice of water out of the tank. So, I mean, it's worth thinking about, why is this an easier problem? Why is it easier to think about just the one slice? The reason is that this entire problem is hard because different parts of the water require different amounts of work. Because the water at the very bottom requires, being lifted up 10 feet to get out of the tank, while the water at the top only needs to be lifted up 3 feet to get out of the tank. So we focus on just one horizontal slice at a time, because if that slice is really thin, we can pretend that all of that water is basically at the same height, and that makes it a lot easier to figure out how much water or how much work is done. Okay. So to lift that red slice out of the tank, what's going to be the work? Well, work is force times distance the force acting on an object is its mass times the gravitational constant g. That's a physics fact, but that's it's the same across all of these work problems. That force is equal to the mass times the gravitational constant. But mass is equal to density times volume. Okay, we're making progress. The density of water, I'm just going to call that rho. We could look up the density of water. It has a numerical value. I don't remember the value off the top of my head, but it's some number. We could look it up. The volume, well, let's think about that slice, and I'll pull it out of the picture to make it easier to analyze. Well, the length is 50 feet, because we're told that the tank is 50 feet long. The height, this is where we should actually start labeling some coordinates. Let's use y as our coordinate system. So the bottom of the tank is y equals 0, the top of the water is y equals 7, the top of the tank is y equals 10, and I'm just going to be looking at some slice, and I will call its height y. And the height is dy. The point is that our y values are changing. Our y values are going to range from 0 all the way up to 7. And the width of the slice is how much your y value increases from one slice to the next. Density of water is just 1. It's 1 if you use the right units. It's 1 kilogram per, well, okay, I think you could say it's 1 gram per centimeter cubed. Yeah, 1 gram per centimeter cubed. Or it's I think 1,000 kilograms per meter cubed. So yeah, we have all these units that we'd need to worry about if we actually want to get a real answer. Maybe we should do that. I think it's worth, in math classes we don't always do this as much as we should and think about the actual, the real world units. You saw how much I panicked a little while ago when my equations didn't have nice integer solutions, but it's worth thinking about, how to actually interpret this, with real world numbers. Alright, so our dimensions are 50 and dy, and the last thing we have to figure out is the width. This is the tricky one, because this changes depending on what y is. When y is 7, for example, at the very top of the water, that's pretty wide. Whereas at the bottom, the width is pretty small. So I'm going to also draw in I'm going to try to draw in that circular end of the tank. Okay, that wasn't too bad. Or I guess semicircle. So I'm trying to figure out this width. And you know, what I want to draw in actually is I want to draw in this line right here. So why did my intuition lead me to draw in this triangle? Well, because this is a circle, or a semicircle. This thing here is a radius of the circle, so I know the length of that. So that would be 10 feet, right? The radius is 10 feet. What did I do to the... Oh my goodness. How did that happen? What is happening to my picture? Y'all are seeing this too, right? I'm not going crazy? Yeah, okay. Oh my goodness. And I can't even erase this? Something's wonky here. I'm going to close this and reopen it. Okay, that looks better. Okay, so that was 10 feet. This side here is the unknown width. I guess it's half the width of the slab. I'm just going to call this X. And this thing here, this side of the triangle, well, this is Y, right? From the bottom of the tank up to the height of my slab of water, that's Y. And then this has to be 10 feet minus Y, because together these two pieces add up to the radius of the tank, which is 10. So if I look at this right triangle, I see that, well, it's a right triangle, so I can use the Pythagorean theorem. X squared plus 10 minus y squared is equal to 10 squared. So x squared is 100 minus 10 minus y squared. And that means that x, well, actually I'm going to simplify that first. This is 100 minus 2y plus y squared. So x squared is positive 2y minus y squared, and that means x is root 2y minus y squared. Yeah, so now we've figured out the width of our slab of water in terms of y. So let's just write that down here. It's 2 times the square root of 2y minus y squared. And that 2 is because there are 2 x's making up the width of that slab. Okay, so continuing to work this out, density is rho, volume is these 3 dimensions multiplied together, so it's 50 feet. I'm going to stop writing the units. We'll just worry about the units at the very end. 50 times the 2 root 2y minus y squared times dy. So that's the 3 dimensions that make up the volume of this rectangular slab. I still need to multiply by g and the distance. I guess I can combine the 50 and the 2 to get 100. The distance is how far I need to lift the slab up to get it out of the tank. If it's at a height of y, how far do you have to lift it up to get it to 10? That would be 10 minus y. So there we go. This is the work that you need to do for to lift that one slab up out of there. What's the total work to lift all of the slabs up? Well, you just add up the works for the individual slabs, and adding them up is as easy as throwing an integral sign in there and making sure to include the bounds. And you notice we've already got a dy in here, so you don't even need to worry about coming up with the differential. You just add the integral sign. So I've got rho 100 times root 2y minus y squared times g times 10 minus y. I'm going to put the dy at the very end. And my y values go from 0 to 7. Rho and g are constants, so they can come outside the integral. And for that matter, 100 is a constant too. So that can come outside. Mean Machine Rex. Probably the easiest way to get in touch with me would be email. I can add my email address here. But yeah, I saw your message. I'd love to hear more about that. So what's still inside the integral? I've got 10 minus y and the square root of 2y minus y squared. Now, a lot of times, we might just ask you to set up an integral and not actually evaluate it. This is a bit of a nasty integral. I think it would, yeah, I got this from a book. It works out a lot better if you make a different choice, which is not the obvious choice at first, but it makes a lot of sense. Instead of referring to the bottom of the tank as y equals 0, so the top of the tank is y equals 10, it actually, the math works out easier if you refer to the top of the tank as y equals 0, so the bottom of the tank is y equals negative 10. So you would be integrating from negative 10 up to negative 3. And the reason that it's better is because we have this circle here. Just, when you do stuff with the circle, it's nicer if you have the center of the circle being at 0 rather than something non-zero. Sorry, it's getting late. I'm starting to lose speed. Lose steam? Whatever, you know what I mean. I am very interested in figuring out how to integrate this. Although, setting it up, I think, is the most important part. So, let me ask the four of you who are still here. Do you have questions about how I set this up? Is there a different topic you'd like me to say something about? Do you want to see me try to do this integral? Are you ready to call it a night? An integral solver? Sure. Yeah, and honestly, I have the answer here, although they did it a different method, so I'm really curious to know if I got, know if my integral computes the right thing. See if I made any mistakes. So I'm gonna ask Wolfram alpha. Oh, this is gonna be ugly. Because I wasn't being super careful with units. What do you say, chat? What do you want to see? Or has this been enough math for one Monday evening? We've been going for about 2 hours. I did not actually end up doing the integral. The problem is, I was relying on Wolfram alpha to handle the units here to try to make it match up with what I have in my book, but this is... I'd have to throw the units in manually. Like that should be 10 meters. I guess this whole integral should come out to... Oh boy, I'm getting real confused about the units. Like, what even are the units here? Because y is distance, but then I have distance squared. But that 2 is... Is that 2 a unit of distance? Where did that come from? No, that 2 is dimensionless. I would have to think harder about the units than I really want to at 10 p.m. But yeah. Maybe I don't need to worry about the units. I just feel like I do. It's the physics major in me that's very concerned about the units. Like, even if I don't need to worry about the nitty-gritty details of how the units work out with all the little pieces here, I should be able to say what the units of the integral as a whole are so that I can combine them appropriately with the units over here to get the correct final unit. Maybe I just don't even worry about that. I just figure out what the final units should be. It's work. So as long as I use SI units for everything, it's going to come out to joules. Is that the trick? No, but I was using feet here. This is just... See, you should just always use SI units. But I think we should call it a night here. Thanks to everyone for joining tonight. If you have suggestions or things you'd like to see in subsequent Monday evening sessions, send me an email. I'm open to feedback. Just what? I'm not quite sure what you mean there. Yeah, send me an email if you have ideas about what you'd like to see. Otherwise, have a great evening, have a great week, and I look forward to seeing you all 1 week from today.